Hello, welcome to Infimix. In this video, I will talk about the conversion of non-deterministic finite automata to deterministic finite automata. So it is the conversion of NFA to DFA. And I will do that by examples. But before we continue, please subscribe, click the bell, like, share, and put your nice comments below. All right now. Without any further ado, let's hit the road. Example 1. Consider this transition graph. It has 4 states, with the start state S, the final state F, and 2 other non-final states U and V. The alphabet consists of the symbols A and B. It is a non-deterministic finite automaton or acceptor. One of the reasons is that, here from state S, there are 2 edges with label A, going to 2 different states. Namely, one goes to the state U, and the other goes to the state V. Another reason is that, from the state U, there is no edge with label A, going out. Now, can you find other reasons why this is not a deterministic finite automaton? So, it is a non-deterministic finite automaton, and we are going to convert this to a deterministic finite automaton. We create a transition table. And later, based on this table, we create the transition graph of the corresponding deterministic finite automaton for this non-deterministic finite automaton. The columns of the transition table consist of the column state and the column of each symbol. Here, column A and column B. The column state will then contain all states of the deterministic finite automaton. We always start with the start state S. From S, where does it go with A? It goes to the state U, but also to the state V. So this is a union of the singleton U and the singleton V. So it becomes the set containing U and V. Next, from S, where does it go with B? It goes only to the state U. Now, we have a new state, namely UV. From the state UV, where does it go with A? Now, to do that, we have to do it one by one. First, from state U, where does it go with A? And then from state V, where does it go with A? Here, from U, with A, it goes to nowhere. We use the empty set for nowhere. And from V, where does it go with A? Also, it goes to nowhere. So we have the union of the empty sets, which is the empty set. So, from the state UV, with A, it goes to the empty set. Next, from the state UV, where does it go with symbol B? Similarly, to do that, we have to do it one by one. First, from state U, where does it go with B? And then from state V, where does it go with B? Here, from U, with B, it goes to the state F. And from V, where does it go with B? Also, it goes to the state F. So we have the union of the singletons F, which is the singleton F. So, from the state UV, with B, it goes to the state F. Next, the state U. Where does it go with A, and where does it go with B? We have investigated this before. From state U, with the symbol A, it goes to nowhere. So it is the empty set. From state U, with the symbol B, it goes to the state F. Next, the state F. Where does it go with A, and where does it go with B? From the state F, with the symbol A, it goes to the state V. From the state F, with the symbol B, it goes to nowhere, so it goes to the empty set. We'll do the empty set last. Next, the state V. Where does it go with the symbol A, and where does it go with the symbol B? We have investigated this before, when dealing with the state U V. From the state V, with the symbol A, it goes to nowhere, so the empty set. From the state V, with the symbol B, it goes to the set F. Finally, the empty set. It is from nowhere to nowhere either with A or B. Now, we are done with the transition table. Next, based on this table, we create the transition graph for the corresponding deterministic finite automaton. But first, we simplify the notations for the states like this. So for example, for the set containing U and V, we just denote it with UV like so. Now, we are going to make the transition graph. Surely, we start with the initial state S. From S, with the symbol A, it goes to the state UV. And with the symbol B, it goes to the state U. Next, the state UV. From the state UV, with the symbol A, it goes to the state empty set. And with the symbol B, it goes to the state F. Next, the state U. From the state U, with the symbol A, it goes to the state empty set. And with the symbol B, it goes to the state F. Next, the state F. From the state F, with the symbol A, it goes to the state V. And with the symbol B, it goes to the state empty set. Next, the state V. From the state V, with the symbol A, it goes to the state empty set. And with the symbol B, it goes to the state F. Finally, the state empty set. From the state empty set, with the symbol A, or the symbol B, it goes back to the state empty set. Now, the final states are all the states containing the original final state F. In this case, only one state contains F, namely the state F itself. So this is the final transition graph and it is deterministic. Example 2. Consider this transition graph. It has three states, with the initial state S, the final state F, and the alphabet consists of the symbol A and the symbol B. This is not deterministic. One of the reasons is that it contains a lambda transition. Now, can you name the other reasons? So this is a non-deterministic finite automaton. We will convert this NFA to a deterministic finite automaton. First, we create a transition table consisting of three columns, namely the column state which will contain all the states for the deterministic transition graph, and each column for each symbol. Here we have symbols A and B, so we have column A and column B. We start with the start state S. With the symbol A, where does it go? From the state S, with the symbol A, it goes to the state F. And with the lambda transition, it can continue to the state V. So here we have the set of F and V. From S with B, where does it go? It goes nowhere. We use the empty set for nowhere. So now, we have a new state FV. Where does it go with A and where does it go with B? We have to investigate it one by one. First, F. From F, where does it go with the symbol A? It goes back to F itself, but it also continues with a lambda transition to V. So we have a union of F and V. Now, from V, where does it go with A? It goes nowhere. So it goes to the empty set. The union of the set FV and the empty set is of course the set FV. So from the state FV, with the symbol A, it goes back to the state FV. So this is a loop labeled A. Now from the state FV, where does it go with B? Again, we investigate it one by one. First F. From F, where does it go with the symbol B? It goes first with the lambda transition and with B to the state S. Note that for symbol B, we have lambda followed by B. Now, from V, where does it go with B? It also goes to the state S. So we have the union of singleton S and singleton S. So that is singleton S. So from the state FV, with the symbol B, it goes to the state S. Now, only one state left. That is the state empty set. But this is easy. We just make a loop labeled AB to the state empty set itself. We are done with the transition table. But to make it convenient, we change the notations of the state sets to this. So, for example, the set of F and V is changed to FV like this. So now, we have these three states. So in the deterministic finite automaton transition graph, we have three vertices. S is the start state. The new final states will be all the states that contain the original final state F. In this case, there is only one state containing F, namely the state FV. So FV is the only final state. Now, from the state S, with the symbol A, it goes to the state FV. From S, with the symbol B, it goes to the state empty set. Next, from the state FV, with the symbol A, it goes with a loop back to the state FV. From the state FV, with the symbol B, it goes to the state S. Finally, from the state empty set, it goes with a loop labeled A, B, back to the state empty set. So this is the final transition graph and it is deterministic.